Hello, my name is Hiroshi Furuya from the University of Central Florida. Today I will present to you autonomous vehicle visual embodiment for pedestrian interactions and crossing scenarios. A wide array of autonomous vehicle, or AV, human-machine interface, or HMI, designs have been created for AV pedestrian interactions. These AV HMIs are frequently preferred by pedestrians who cross the road in front of the AVs. We know from human-robot interactions research that human-like visual embodiments can help people interact with robots and autonomous systems. So in this work, we aim to apply those techniques to AV HMIs for the purposes of autonomous vehicle pedestrian interactions. In this work, we also use virtual reality, or VR, to both prototype the interface as well as to replicate the traffic scenario. We address the following research questions. 1. Can virtual visually embodied agents, henceforth referred to as virtual drivers, be used as AV HMIs to improve AV pedestrian interactions in a crossing scenario? 2. How do human-like behaviors impact pedestrian experiences? This work culminates in the following contributions: an artifact of virtual driver as AV HMI in VR, an experiment with the aforementioned artifact studying its impact on pedestrian crossing behavior, and empirical evidence demonstrating pedestrian preference for this virtual driver. We answer these questions using the following user study. We had a 3x2 within-subject factorial experiment with a randomized complete block design with 26 total participants. The experiment had the following independent variables, the first being the state of the virtual driver. This independent variable had the following levels: no virtual driver, a virtual driver that is completely still, we call it the static driver, or a virtual driver that looks at the pedestrian in the crossing scenario. We can see these three conditions at the bottom. On the left-hand side, we see an empty car, that is no virtual driver. In the middle, we see the virtual driver completely frozen, looking straight ahead, that's the static driver. And on the right, we see the virtual driver looking straight at the camera, which would be the driver looking at the pedestrian in the crossing scenario. The second independent variable is whether the car stops for the pedestrian at the crossing scenario. And this has two levels: the car does not stop at all, or the car does stop. We have the following dependent variables: the time it takes for the pedestrian to cross the road, TTC, the time it takes for the pedestrian to decide to begin the crossing maneuver, called the TTD, the reported safety rating that the participant gives to describe how safe they felt during the whole interaction, and the pedestrian's subjective preference for AV HMI condition. This picture illustrates the crossing scenario. We see an AV approaching a zebra-striped crosswalk with the participant on the right-hand side inset looking towards the virtual car. We see another angle of the same setup, although with a different participant. We see the participant on the right side of the screen standing in front of the crosswalk, looking off to the left at an AV with the virtual driver approaching the crosswalk. Here we can see our results. We did not find a significant effect of AV HMI condition on time to cross, although we did observe a significant effect of AV HMI condition on the time to decide to cross. We did not observe a significant effect of AV HMI condition on rating of safety. Of the 26 participants, 25 of them preferred most the condition where the virtual driver looks at them, with the last participant preferring no virtual driver at all. Of the 26 participants, 15 of them preferred least the condition where the virtual driver was frozen in place, with the remaining 11 preferring least the condition where there was no virtual driver at all. Some participants gave us the following thoughts. The virtual driver looking at them made them feel like the car was aware of their presence, but when the virtual driver was frozen in place, it made them feel the very opposite, that the car was completely unaware of their presence. Participants also gave us some suggestions for additional AV HMI features that they would like to see. For example, front-facing brake lights, speed indicators, or even additional gesturing from the virtual driver. We have the following takeaways. There is a noted preference for the virtual driver AV HMI, but only when it behaves in a satisfactory manner. This high sensitivity to the human behavior of a human-like agent is somewhat similar to the sensitivity that we observe in the uncanny valley. Another takeaway: the interface recommendations for our participants are similar to designs that we've seen in literature. This would motivate future work combining the two techniques. Lastly, we found that participants' verbal comments about how safe or aware that they felt the situation was contrast with the generally flat but high mean safety ratings. This may signal that VR might not be as ecologically valid as we thought it would be for this experiment, or perhaps that our method of collecting feelings of safety may need to change. In conclusion, we've demonstrated this artifact for the virtual driver AV HMI in VR. We've found that participants prefer having the virtual driver look at them. We can expect in the future that advanced display technologies can allow every AV to perhaps have their own virtual driver as an AV HMI to help communicate and interact with pedestrians and other traffic actors. This work takes the first step in understanding the impact that these interfaces can have on society and other members on the road. Thank you very much.